Hey, how's it going? So I'm Matt, I do containers and stuff. Today we're going to be talking about linked lists, specifically one linked list in particular, this linked list. It's a PLF list, which is a more contagious linked list, which is a drop-in replacement for standard list, and it's not quite so bad as standard list. It's open source, permissive license, so you can pretty much use it for whatever, and you can download it there. So, first question, why did I spend about 6 months or so developing this thing? Why develop a contiguous linked list? The answer to that is, not that I'm comparing myself to the great Sir Edmund Hillary, climber of Mount Everest. Although, no. But about a year or so ago, a guy got in touch with me. He was using my other container colony as a way to build a contiguous linked list in memory. And I thought, oh, that's an interesting idea. It's a very inefficient way of doing it, but it's an interesting idea. So I spent about 3 or 4 months sort of on and off thinking about this problem, trying to come up with the best way that I could think of to do the same thing. And that kind of worked out. And the results are cross types on Haswell under GCC. We're talking types, talking char, double, int, small struct of 20 bytes, large struct of 270 bytes. So 333% faster singular insertion, 81% faster singular erasure speed, 16% faster iteration, 72% faster sorting, and 25% faster overall in ordered use case benchmarking. So, I mean, my testing range has been relatively limited at the moment. It's been on Haswell and Core 2 Duo. I haven't done a lot of cross-compiler testing as yet to see if there's any sort of deficiencies in the others. So I haven't had time, but I will get onto that. So how do we do that? First thing is to unroll the list. So instead of allocating our nodes individually in the linked list, which is sort of the typical implementation, you allocate them in node chunks, and this is known as unrolling the list. So obviously all the smiley faces are elements and vectors and arrays. They're all in one nice chunk. But most lists and maps, etc., are all over the show in memory, unless you're using some kind of allocator which is doing smart stuff. And unrolled lists, dex, and colony, my other container, are segmented in chunks in memory. So if we unroll the list, we can also do fun things like reusing the nodes from previously erased elements, and that reduces the amount of allocations and deallocations that we're doing. And we also use an alternative sort technique. So to understand why having a more contiguous linked list is important, we have to go back in time a little bit. So just hold off thoughts of your impending mortality for a few more nanoseconds while I explain some things. So back in the late or mid to late 1980s, where the general ideas for what would eventually in the 90s become the STL were forming in people's minds, the difference between memory and CPU speeds were not as great as they are today. But over the years, CPUs went like that, RAM went like that, and we have this ever-increasing gap. And we've sort of hacked around that on the hardware level by using cache, but that has some limitations. So to get things working well with the cache in memory, generally we want to have things contiguous in memory. So when we read that first integer, it goes to main memory, CPU grabs a chunk from main memory, that goes into the cache, and then when you read the second integer, hopefully it was contiguous in memory with the first integer, and therefore it's already in the cache, and you speed up that operation of fetching that integer by approximately 100 times, depending on your CPU and that sort of thing. So that's why, particularly over the past 10 years, there's sort of been a catch cry of just use vector, at least in a lot of fields. In some fields, not so much. Like gaming, we tend to say just don't use vector, except for these situations where you can get away with it, but not so much in these scenarios. Whereas the catch cry for linked lists has been more along the lines of linked lists, good God, y'all, what are they good for? Absolutely nothing. Much like Windows 10. That's right, Microsoft isn't sponsoring this conference yet. And having said that, they probably never will now. Anyway, so obviously there are actually some problems with linked lists. They can't leverage SIMD. Assuming an Intel-type processor, SIMD, so SSE, AVX, the things have to be contiguous in memory. So that actually also goes for all standard library containers except for vector and array, to the best of my knowledge. They reduce the benefit of out-of-order execution, and they throw off hardware prefetching, which kind of come down to the same thing. When you're reading the next node in the linked list sequence, to get the address of that node, you have to have already read the first node. And to know where the third node is, you have to have already read the second node, etc. So prefetching doesn't work as well as it does with something like a vector or whatnot. They reduce DRAM and TLB locality, and they are harder to send to GPUs. And I would add to that, following pointers to other pointers results in poor iteration performance, as the CPU can only cache a limited number of jump destinations. So at least in terms of the tests that I've done on Haswell, there seems to be reasonably high cache for jump destinations, whereas if you go back to Core 2, it's almost nothing. So it does very little, but anyway. And there's always going to be, in a real-world program, when you're not doing benchmarking, there's always going to be competition for that cache as well. The sort performance is not actually that great, except for large or non-trivially copyable or movable types. Insertion and destruction are slow due to the individual allocations, deallocations, and it's bidirectional iteration only, so no indexing. And yet, that same website that I grabbed data off 2 slides back, it got its data from another website, and when that website was still online, which is not now, it had a poll on it from 2010 where it asked people, are you still using linked lists? And 60% of the programmers there said yes. Now, obviously, over the past 7 years, there's been a lot more communication in the C++ community, in particular about memory locality, this sort of thing, why that's important. But still, there must be some reasons why people are still using them for something. So what's good? If you're doing it via an iterator or during iteration, they have the fastest singular erasure speed of any of the standard library containers. They have the fastest non-back, non-front ordered insertion of standard library containers. They have the fastest individual insertion and sorting for large or non-trivially copyable types. Iterators and pointers to non-erased elements stay valid regardless of operation. Now, obviously, depending on your field, that either is or isn't going to be important. If you're doing a lot of modular work, so you have a lot of elements in containers which reference other elements in other containers, that becomes more important. So it doesn't matter if you're splicing, erasing, inserting, merging, etc. All your pointers to elements stay valid. You have O1 splicing together of lists. So for anybody here or on the YouTubes who doesn't know what a splice is with list, so you have list A, list B. List A says to list B, hey, have some of my stuff. And list B says, hey, sure, thanks. And all that gets changed is just a couple of previous and next pointers. So there's no actual copying of data. So it's a very quick operation, and all of those pointers to elements still stay valid even when they're in the second list. It's also relatively easy to create concurrent versions of linked lists for reasons that are beyond the scope of this talk. There are a lot of things that are beyond the scope of this talk, but if I were to list them all, that would also be beyond the scope of this talk. So that's all well and good, but where will this actually be faster? So any ordered situation, and when I say an ordered situation, I mean a situation where the order of your elements is important. So when we're iterating, we want things to be in a particular sequence. So any ordered situations with a lot of non-back, non-front insertion and erasure, we've got a lot of splicing or merging, large types, and a lot of sorting, objects that have significant move or copy costs, and they're also useful for non-copyable, non-movable types. So if you're using a vector or whatever, as soon as you insert into the middle or erase, you're creating reallocations, and obviously you can't do that if you've got non-copyable, non-movable types. Incidentally, for any of that stuff, if you've got an unordered situation where you don't care about your iterative sequence, Colony will be a faster container for that. So who here knows what an intrusive list is? Yay, some people. Okay, so for those who don't know, an intrusive list, essentially, the main use case, as I've heard it, is you have process B, you have process A. Process B has a container of some description. and the elements in that container inherit a base class, which contains previous and next pointers, and a little bit of code. Process B doesn't own that container, but it can form a linked list out of the elements in that container. And the nice thing about it is that basically the little bit of code that you've got in the elements says that, okay, when an element gets erased from this backend container, it's also going to automatically take itself out of that linked list owned by the second process. So it's quite good for when you've got data that belongs to one thing is being accessed by another, concurrent situations, this sort of thing. But it's not really a replacement for standard lists. And the reason for that is that generally the backend container is something contiguous, like a deck or a vector. So it's not going to have tremendous performance when we're talking about insertion and erasure to the middle of the container, which, as specified before, is one of the only nice performance points for linked lists. At the same time, you still get the same iterative performance of a standard list, so you're kind of getting the worst of both worlds in terms of performance advantages. It's a little bit more complicated than that. I could go into all the side cases, but that's kind of an overview. So if we can actually own the data, we're going to get better performance in general if we use a linked list, provided we make the linked list relatively smart. And as a side note, if the backend container doesn't get erasures from the middle, then we're probably going to be better off, instead of using a linked list, having a vector of pointers instead. I've talked to some people, and they've kind of gone from having intrusive lists to having vectors of pointers in certain scenarios, and you basically get a speed up of about 2 times, at least in their case. Obviously, there's lots of edge cases and different scenarios, so by no means one size fits all. Anyway, that's just to establish that we can't replace standard lists or their usage with an intrusive list without some significant performance costs. So how do we improve upon the standard list? The first thing we need to do is remove range splicing. So you can have a full splice where list A goes, have all of my data, and you can have a partial splice where it goes, hey, have a little bit of my data. Now, the problem with doing that is as soon as you start allocating your nodes in chunks, then you end up with a scenario where you've given some elements to here, but some of those elements belong to this memory chunk here, but some of the elements in that memory chunk still belong to list A. And then you end up with a scenario where you've got a memory chunk that's owned by 2 different lists, which is just in all sorts of different things, nightmare, concurrency, and whatnot. So we don't do that. So we just remove partial splicing, which then allows us to allocate our nodes in chunks. In turn, allows us to reuse nodes from previously erased elements. And we do the sort hacking. So I'm going to go over the sort hacking first, because that's kind of, well, to me it's fun. It's probably going to be boring as hell to you, but I'm going to do it anyway. So this is the process I came up with that enables you to take any bidirectional container and use sort techniques that typically require a random access iterator, so standard sort and that sort of thing, any quick sort algorithm. What you do, it has a cost, which is a temporary array of n pointers, 1 for every element. But across types, it's about 72% faster than sorting within standard list. It's still not as fast as sorting with a vector plus standard sort, except for large structs and smaller numbers of small structs. You could use stable sort if you want, if order-stable sorting is important to you. And I use this same process with colonies. So the basic process is you create a temporary array of n pointers, and you fill the array with pointers to each element in your container, whatever it is. And then you sort the pointers themselves, not the elements, but the pointers, by the elements that they point to via a dereferencing template functor, and that's what that looks like. I didn't come up with this particular thing. My template foo was not strong enough. I had to consult Dr. Stack Overflow, and for that I apologize. So once you've done that, once you've sorted the pointers, you process the results, and this step kind of varies based on the container involved, and then you delete the temporary array. So in terms of that third process, basically what we do is we take that array of pointers, and for every pointer at index I, we dereference to the node and we set the previous and next pointers to the pointers in the pointer array at I-1 and I+1 specifically. And we just do that right across the array. And then we set the node pointed to by index 0 as front node, and the node pointed to by the last index as the back node, and then we're done. So moving on to list unrolling, allocating nodes in chunks. Obviously, this increases memory locality and cache performance for iteration, and it reduces the overall insertion, erasure, and destruction costs by having fewer deallocations and allocations. How we do that with PLF lists is we have an internal vector of groups, which in this context I take to mean a pointer to a memory block plus metadata about that memory block. Memory blocks start small and have a growth factor, just so that we have sane allocations. So when we're inserting into the list for the first time, we don't want to allocate enough space for 100 elements or whatever. So we keep it small, maybe 8 or 16, expand from there. And then we keep the maximum size of these memory blocks relatively low to allow for better reinsertion, which I'll get to later on. But first of all, erased nodes, obviously, we can't reallocate like we can with a vector, because then we lose our validity of pointers. So we've got to find some way of keeping track of these erased nodes and reusing them. Okay, so when we're inserting into the middle of the container, and there's no reusable nodes available, so nothing's been erased at this point, we've got no choice but to insert to the end of the last memory block. Now that's okay, there's not really too many ways around that, but what we end up with is an iterative sequence in memory which looks like jump, jump, like that. So we want to avoid that as much as possible. So we want to reuse nodes, and specifically we want to reuse nodes that are as close to the insertion point as possible, because we want to try and keep that iterative sequence as linear as possible. It's not going to be completely linear, assuming you're doing a lot of erasures and insertions, but we want to keep it more linear. By the way, everything that I'm kind of telling you here is based on the benchmarking that I've done, not sort of theory. So I don't have a lot of time for theory. So we need to have a strategy, A, to keep track of where these erased nodes are, and B, finding the nearest one to the insertion point. So I came up with 3 different strategies, and over about a month and a half, tried all 3 of them. First one is a reverse jump counting skip field. This is a numeric pattern which allows iterators to skip over runs of erased nodes. So in terms of the sequence that's up there, that's 0, 0, 1, skip 1, 0, 0, 4, skip 4, etc., etc. One of the secondary properties of this is that from any skipped node, you can quickly find the nearest non-skipped node. So if you take the 3 there, that tells you that the nearest non-skipped node to the left is 3 places away. From that, we also know where the start of that run of erased nodes is, so the 4, and that tells us where the end of the run of erased nodes is. So if we use that concept, we can basically use it in reverse with a linked list. Won't go into it in too much detail, to find the nearest erased list node from any given non-erased insertion point. So I tried this and it worked fine, but the problem was that using this sequence normally is fine, but when you reverse it, when you use it to indicate that every skipped node is in fact a non-erased node, the update sequence of it turned out to be too inefficient overall. So that didn't work out so well. Second strategy I came up with was a global free list. Who here doesn't know what a free list is? One person. That's all good. I'll explain it anyway. So free list, you have your free list head, which is a pointer. That points to an element. That element is generally unioned with a pointer, and the unioned pointer points to the next erased element, and to the next erased element, and so on and such forth. That doesn't work out so well for generalized containers because unions in C++ don't support some very basic class functionality. But for a linked list, it works out fine because you've already got the previous and next pointers there, so you don't actually need to union anything. So in this case, basically having a single free list head that points to the last erased node, which points to the next one, etc., etc. The advantage of this process is that it's very quick to push and pop these erased nodes from the free list. The disadvantage is that it's quite slow to find the nearest erased node to the insertion point. You basically have to iteratively process the entire free list, and assuming a random erasure sequence, that means that you're jumping all over the place in memory, and it's not very good for your cache. So that turned out to be not as fast. The other thing is that when we're erasing lots of stuff, when we basically erase all of the nodes in any of these node blocks, if the node block is reasonably small, we kind of want to free it to the OS. That's just so that we don't have too many small blocks running around and we have more larger contiguous blocks in memory. So if we do that and we've got a global free list, then again, we need to process the entire free list to remove the nodes of that node chunk from the sequence. So again. So the third strategy was to do free lists, but to do them per node chunk. So basically, the free list head becomes part of each node group's metadata. And when we are inserting into any given particular point in the list sequence, we get that insertion iterator that tells us where we're inserting to, tells us where the node chunk is. And we look at the free list head for that node chunk. If it's null, we have to search outside of that node chunk. But if it's not null, then we just grab the first erased node off that free list head. So that's very fast. But if we're having to search outwards from that node chunk, then again, we need a third strategy. So we can just scan all the blocks. I mean, there is a counter in memory that says, okay, we have some erased nodes or we don't have some erased nodes. So we check that first, obviously. But if we do have some erased nodes and there aren't any in the node chunk that's pointed to by the insertion iterator, then we can either just scan all of the blocks from front to back or back to front, or we can kind of start scanning left and right from the node chunk that we're currently at. Turns out that the latter one is faster, partially because we end up getting to places that are closer in the iterative sequence faster. And there's a bunch of other hacks that we can do for that, like storing a pointer to the last used free list head that actually wasn't null and this sort of thing, but I won't go into that. So a couple of additional notes. The nodes chunks, as I said before, we have to keep them at a reasonably small size. If we make them too large, as you can imagine, if we're using per node chunk free list heads, then we have a node chunk that's maybe 16 million elements, and then we pop a location off the free list head, and our insertion place is here, but the place that we've gotten off the free list head is here, then that's not so good either. So I did about a month or so of benchmarking across compilers, across platforms, and across different types. And overall, what I found was roughly about the best maximum size was around about 2048 elements. It's probably not exactly that, but as a programmer, I crave powers of 2, so I just rounded it to that. And the second note is having these node chunks in memory. It means for some operations where we don't care about the iterative order, we can actually just linearly iterate across those node chunks, which ends up being betification, this sort of thing. So sorting, we went over that. Destruction is one obvious one, but also reversal, remove if patterns, this sort of thing. But if we're doing that, we need a unique identifier to specify, okay, this is a normal list node, and this is a node which is part of a free list, so it's been erased. So what I did for that is free lists only need one pointer, they don't need two, so I just made the previous pointer to be the one that's used, and you make the next pointer equal to the previous pointer, and that's the unique condition. It works pretty well. So, now that I've bored you all to tears, you're asking, have I got anything interesting? And the answer to that depends. Do you like benchmarks? If not, you are screwed. So, all of these are under GCC, O2, native on Haswell, and both axes are logarithmic. Only going to do three types: integers, small struct, and large struct, because otherwise we'll not quite have enough time. So the green is standard list, and the orange is PLF list. So obviously you get a significant advantage when you're doing that initial insertion, because you're doing fewer allocations. Small structs, very similar. Large structs, you always seem to get some weirdness in terms of performance. I suspect it's something to do with the size of the type, overflowing cache boundaries or something, I don't know. But you do start to get a little bit of kind of crossing over between the PLF list and standard list performance, but overall it's faster. So erasure, I haven't included Removeth results for vector and dec here because this is singular erasures. But I have done the results for Removeth, and they are basically the same as PLF list, but just very slightly more, very slightly better rather. So this is erasing 25% of all elements while iterating across the container, raising them at random. So PLF list faster than the others, a little bit of crossover above 100,000 elements. And then large structs, we get, again, a little bit of that crossover weirdness between standard list and PLF list. I have yet to work out exactly what that is, but perhaps somebody in the audience who is more familiar with cache, etc., can tell me. Iteration, so yellow is standard dec, standard vector is sort of hidden under the standard vector results, very similar. Large structs, we sort of start to see things expand out a little bit. And then large structs, we start to see a little bit more of that crossing over of performance again between standard list and PLF list. So, sorting, integers, standard list not doing too well, PLF list doing roughly about the same as dec up until around about 1,000 elements, then it gets a little bit worse. Small struct, PLF list is about the same as vector plus standard sort until you get to around about 5,000 elements, and then it starts to get a little bit worse. And then large structs, both standard list and PLF list doing a lot better. The obvious reason for that is with a large type, with sorting with a standard list, you're not actually moving the elements around, you're just changing pointers, previous and next pointers, so no copying, and obviously that makes a difference for large types. So that's all very well and good, but that's micro benchmarking. So just going to go into a little bit of actual, semi-use case benchmarking, simulating real life, whatever that is. And here we're basically simulating a scenario where we have 60 frames per second in some given application. And for every frame, we're iterating over the data once. And for every minute, that is every 3,600 frames, we're erasing and inserting 1% of all elements at random places in each container. And we do that for half an hour of simulated time. So down the side there, we've got PLF list, standard vector, and standard dec. I've also included a few container modifications there. In this case, so there's pointer dec, which is a deck of pointers which point to the elements in a deck of elements. And when you erase from that container, you erase from the deck of pointers, not from the deck of elements. And provided you have a large enough type, that enables you to reduce your reallocation costs when you're erasing or inserting to the middle of the container. Similar thing for index vector, it's just a vector of indexes to a vector of elements. And pointer colony is a similar concept. Colony, the container is unordered. So in order to make it ordered, basically have a deck of pointers, and each pointer points to an element in a colony of elements. So for erasing and inserting 1% of all elements per minute of time, both of the linked lists are not doing as well, though PLF list is doing better. If we increase that ratio to 10% per minute, it's still not doing as well. Basically, all of them have kind of expanded out a bit. So basically what we're looking at is at this point is an iteration to modification ratio. So at the moment, our iteration to modification ratio is relatively low. So what happens if we up the modification side of it? So we go to erasing and inserting at random 1% of all elements per frame instead of per minute. Suddenly we get quite different results. And by the way, I've only included Removeth results for some of the other containers because we're erasing a lot of elements, so it's faster for those containers to use the Removeth idiom. So immediately we see both of the linked lists performing quite significantly better than the others, basically because they don't have those same modification costs. And if we up that again to 10% of all elements being, which is kind of ridiculous, but for the sake of argument, we'll go with it, up it to 10% per frame, then again we get a much greater increase of performance for linked lists. And that is, thankfully for your sanity's sake, the end of the benchmarks. So, do the use cases for linked lists change with having a linked list that performs a little bit faster? And the answer is a little. So mostly we're just improving on the overall performance of standard list when we're using PLF list. But that in turn decreases the threshold at which point we might consider using a linked list. So the threshold in this case is basically your modification to iteration ratio, provided you're talking about an ordered scenario. So as soon as you bring the overall performance of a linked list up, that threshold becomes lower. Also from using the different sort technique, instead of just not wanting to use a list for sorting at all except for large structs, we now can say, okay, if we've got medium to large structs, the linked list is going to be faster, and if we've got smaller amounts of small structs, so less than 5,000, it's also going to be faster than using, say, a vector plus standard sort. So the outcome of that benchmark, of those benchmarks, is basically to say, if you've got a fairly strong modification to iteration ratio, maybe think about what a linked list could do in that scenario, depending on what the scenario is. So, could standard list be more like PLF list, i.e., could PLF list be considered a valid implementation of standard list, or could we modify standard list so that PLF list could be a valid implementation? And the answer is no, unfortunately. So, as mentioned, we can't have any partial splicing. So that's one thing that has to be removed, unless somebody comes up with a really, whiz-bang solution for that, which I haven't been able to think of. Singular erasure and insertion times are O1 amortized instead of O1. It doesn't actually matter because they're still a lot faster, but for some people, time complexity is something that matters to them. To me, it doesn't. It seems very theoretical and not terribly relevant on modern hardware. But anyway, there are some new functions. The standard sort of stuff that we get with any container that has memory chunks or one memory chunk. So shrink to fit, capacity, reserve, and there's also a secondary function I've included in there which is called reorder. Reorder is basically like a intra-list splice. So instead of taking elements from one list and giving it to another list, you're basically taking your one list, taking some elements within that and saying, hey, elements here, you need to be here now. And you can just do that in O1 time without copying because you just change a couple of previous and next pointers. I'm not sure why that isn't part of the standard already because it seems like a real no-brainer, but anyway. Personally, I would probably deprecate the requirement that the sort algorithm be order stable, given that order stable sort algorithms are generally slower, but there's probably some technical reasons why that was designated to be order stable with linked lists, which I don't know and I haven't been able to find out. So, also with any linked list that uses node chunks, it's harder to make a multi-thread safe version, i.e. concurrent. Because you've got the additional metadata, you're kind of updating a little bit more stuff when you're doing erasures and insertions, so you've got to have mutexes or something over that to protect them. So a proposal for like a standard 2 list or a standard segmented list is possible, but not an amendment to standard list itself. So, what I hope you've gotten from this talk is mainly that there are actually legitimate use cases for linked lists purely from a performance perspective and not just from a usability perspective, intrusive and otherwise. In most cases, when you can and when you can get away with it, you should use a more contiguous container because generally speaking, across domains, the performance will be better. However, if you think outside the box, you can make a better linked list. And if you have a high ordered modification to iteration ratio, you should think about it a little bit. So thinking about outside the box leads me to my final point, which is ignorance is bliss. So when I started this project, I didn't know anything about any contiguous linked lists that had been made in the past. So I didn't know that one had been done in the JavaScript, one of the JavaScript libraries that also uses global free list heads, this sort of thing. And if I had known this stuff, I probably wouldn't have tried. But there is a general problem with programming being a high knowledge, low ignorance domain, which is that if you already know, or people keep on telling you, this has been tried before, this is the way we've already done it, this is the best way to do it, you probably won't start thinking, okay, how can I do this better? So because I'm a complete ignoramus, I didn't know that, so I came up with some new ideas which turned out to be kind of fun, like per node block, free lists, and that sort of jazz. So if people, and particularly students and that sort of thing, are told, you know, this is the best way to do things, it's all been tried before, they're probably not going to try any better and find out things that haven't been done. An example of this is something I've seen on Stack Overflow and a few other places a bit, which is people talking about decks and how, you know, you can't have a deck with a growth factor because then indexing won't be O1 and your plus equals operators on your iterators won't work correctly. Or they won't be O1 and this sort of thing, and that turns out to be false. You can actually do that with some bit shifting hacks and just keeping your node chunks in powers of 2. It's totally doable. But I'd been told that so many times that I just assumed that it wasn't possible. So for a long time, I didn't question it and I didn't think about it until I did think about it a bit, and then I thought, oh, wait, no, wait, yeah, no, you can. So that's why a friend of mine, who I will not name, for he has a bad reputation on the internet, and it is well deserved, when he's not saying incredibly crass things about millennials, he occasionally says some wise stuff, and one of the things that he says is that young people are the best for invention. He was specifically talking about programmers, but I think young people in general. That's because they don't have all the rules in their head, so they're the ones who run through walls without realizing that the walls are there in the first place. Now, obviously, that has its limits. Anybody who's dealt with a lot of younger programmers will know this. But if you fill in too many of the blanks in people's heads, there may not be a lot of room to move and for people to come up with their own ideas. So in the talk on this quote, this is Peter Drucker talking about World War II. So the Allies' ships were getting bombed rather an awful lot, and in particular their supply ships were getting bombed rather an awful lot, to the extent that they couldn't build an awful lot of boats to replace the ones that were getting bombed. So they turned to the Americans. The Americans at that point in time didn't quite have the shipbuilding history that they had in Europe, at least not to the same extent. So the guy that they got in charge of the whole operation was called Kaiser, and he didn't know anything about it anyway, and nobody under him knew anything. And because of that, he didn't know that you needed all this heavy machinery in order to cut all the metal pieces to the exact shapes and specifications to fit to each other. So he just got his workers to use blowtorches, essentially. And that ended up being a lot faster and cheaper. And along the same vein, he replaced riveting with welding. That turned out to be faster and cheaper. And so they were able to churn out these ships in not quite a fraction, but significantly less time than the English could. And that is part of what helped win World War II. So because they didn't know any better, they were able to do better. And that's what I got. So, thanks. Questions? Yep.
Did you get a chance to compare study list using allocators with PLF list?
No, I assumed that using any halfway decent allocator, you would get a sizable performance advantage. However, having said that, if you're using an allocator, I'm not sure that it would be able to infer, for example, from an insert operation, it's not going to be able to exactly grab that iterator and go, okay, that's where this guy is in memory. That means I need to grab this node in memory. So I think there would be a performance advantage there, but not to the same extent.
There is a hint parameter to std allocator.
Right.
Which could have helped.
Could help, yeah. But no, the answer is I haven't tested. Yep.
Just wondering, do you know what the effect of smaller cache sizes would be on the results that you showed, like around PLF list and standard list, say for embedded applications or on mobile platforms?
Right.
Processors have a lot less cache than modern desktops.
Yeah. Yeah, obviously if you've got that kind of scenario, then you're not going to get so much advantage from the cache, in which case contiguous memory doesn't matter to that much in the first place. So in that case, you're not really worried anyway. So yeah, it's not going to have as much of an advantage on any situation where you're not using cache at all, I would assume. Yeah. Aside from the fact that obviously you're doing fewer allocations and deallocations, so depending on your platform, most platforms that should make a difference, but how much of a difference it makes, yeah, comes down. Yeah.
So what is the pathological case for PLF list? Like, how bad is the worst? For example, so if, let's say IPS is when you have your pointers in reverse, so the cache look ahead doesn't work as well, and when you're trying to do iteration through that, how big?
In reverse, it wouldn't be so bad because you're still, if you've got that and then it's reversed, then essentially you're going backwards, but you're kind of reading stuff into the cache that's still relatively linear in sequence. The worst case scenario is where your thing is filled up, you haven't done any erasures, so you start inserting randomly to different places in the list, and that all ends up going to the back, obviously, because there's no erased nodes. So then you end up with the iterative sequence, which is something like jump, 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 jump. That's the pathological case. Yeah. So we're kind of, in order to get best case scenario performance out of it, we are assuming that you're going to be doing some erasures. However, having said that, again, doing fewer allocations and deallocations, you're certainly not going to be doing any worse than you would with standard list.
Do you have any comments about what you learned about the benchmarking process? Because I was just thinking, like, there's sort of two sides to the whole research aspect, which you are very cool, by the way, I think.
Thank you.
But I was just having a look online trying to find out if FFmpeg used std list. So what would be super cool is to write a Perl script that stuck your container into some popular open source project that used containers and just
Right.
see what happens in real world, say video decoding, benchmark, something like that.
Yeah. I just realized I haven't been repeating the questions for the sake of YouTubes. So just before I go into that one, I'll just recap what the two previous questions were. So they were...
Allocator.
Yep, whether or not I've used an allocator, benchmarked against using an allocator with standard list instead of PLF list, and
The effects of cache size on the results.
and the effects of cache size, for example, on embedded platforms where you don't have a lot of cache. And your question was the most pathological case and whether that would be sort of reversing the list, that sort of thing. Your question is basically whether or not I've contemplated plugging it into something else and seeing whether it's made a difference. I haven't done that as yet. I can't imagine there's too many. I mean, there must be some open source projects out there that are using linked lists. I just can't think of what exactly they would be or how I would even go about finding out which field uses linked lists more and that sort of thing. Would be interesting to see how that turns out. And then your other question was about whether I learned anything from the benchmarking process. Most of what I learned, I actually learned when I was benchmarking Colony, which is my other container, which is essentially designed for high modification, unordered scenarios. And the main thing I learned is that it's kind of hard. Like, you'd think that it would be stupid easy to benchmark stuff. You just go loop it a bunch of times and this, that, and the other. But there's quite a few things that you have to get your head around and learn before you start benchmarking things properly. And I was certainly guilty in the early days of Colony of putting out some benchmark results that were completely false, not because I was falsifying them, just because I was an idiot. So nowadays I'm much more stringent about what I do with my benchmarking. A few things that I can just name off the top of my head would be having a decent package for actually measuring the time. I ended up writing my own one, nanotimer, just because Chrono and that sort of thing at the time when I was working on it didn't have good cross-platform support. That, obviously you're looping over stuff tons and tons of times. One of the things that is kind of not entirely intuitive is, particularly for stuff like this where we're judging iterative performance and that sort of thing, kind of helps if you do a whole bunch of runs first and then discard them and then do the rest of your runs and measure that. And that just means that your cache has kind of been warmed up for the specific operation in question. Yeah, hopefully that answers enough of what you were saying.
So is there another push operation that's not sort of just push front or back that you've got from sort of pushing to the empty spot?
Sorry, say that again?
Is there another push operation that you've added into the list to be able to push into the empty slot rather than front or back or insert into the iterator?
So the question is whether there's, like, you can correct me if I'm wrong, but I think the question is whether there's a separate function for inserting to these erased node slots rather than inserting to the back. The answer is no, it just automatically reuses the erased node slots if there are any, and if it doesn't, then it chucks them to the back. And it just tries to find the closest one without wasting too much time in the search. Yeah. Anybody else? Then I think we are done. Thanks, guys.